In the previous lecture, what we had seen was essentially the idea of, so we had this feasible set for the linear programming problem. And somehow we had found a vertex of the feasible set, and we had all these neighboring vertices. And computationally, we wanted a method to traverse from this vertex to a neighboring vertex without any reference to any cost function. So that was the first step. And using the like the computational description of a vertex of f as a basic feasible solution, which would correspond to some of the columns, linearly independent columns of this matrix A, A1, A2, AN being these columns. So first we figured out a way how to move from this vertex to this by choosing a non-basic column. And then the cost function entered into the picture, because the strategy essentially in the simplex algorithm is to move to a cheaper vertex. So we had to incorporate that into our picture in order to figure out what non-basic column should I choose, or in terms of the geometric picture, which neighboring vertex should I choose to move to. All right, so just as a quick reminder, so we had computed the updated cost, and looking at that, we had this expression that updated cost minus old cost is equal to theta naught times Cj minus summation I equals 1 to m Cbi xij. Yeah.
Sir,
And
I
so,
have a doubt.
sure, please go ahead.
Yeah, so you told that if you are having two neighboring vertices, then there will be n minus one linearly independent constants which will be common to them, at which they will be tight.
Right.
So how that corresponds to m minus one independent columns?
Okay. So, so it's about k dimensional faces. So k dimensional faces. So it's more general than that. So we were just interested in vertices, but I can make a statement of a more general nature, saying that a closed k dimensional face of f or a general polytope or a polyhedron. So a closed k dimensional face of f is determined by, so for example, for a vertex, I would, so k dimensional face, if k is 0, then 0 dimensional face is precisely what means to be a vertex. And for the vertex, we have shown that any vertex corresponds to, you need n linearly independent constants which are tight, where that point is tight. So for the k dimensional face, that is determined by n minus k linearly independent constants, and all points of that face are tight at these constants. So all points of that face are tight at these constants. So the proof would be quite similar. There we had used the fact that the rank of that the matrix of those constants is equal to m. So you can review the proof, and hopefully intuitively this looks believable. So for example, this edge between, like, the line joining these two vertices, this is actually a one-dimensional face. If v1, so let's call this v1, let's call this v2. If v1 and v2 are neighboring, you can take this as a definition, but I'm just saying that intuitively, when you look at the geometric picture, if v1 and v2 are neighboring, then this is a one-dimensional face. If it is not neighboring, for example, I had drawn this picture, you have these two tetrahedron, and then let's say you join them together. So this is also a polytope. So here, these two are not neighboring vertices. These two are not neighboring. If I join the line, or if I construct the line segment with these two vertices as the endpoint, then the whole line segment is lying in the interior. It's not really this edge, not a face, not a 1D face of f. But these edges are 1D faces. So these are actually, yeah, these are the one-dimensional faces or edges of this feasible set F. So that's why these two are the neighboring vertices. So yeah, so coming down to the question asked was, how do we know that n minus 1 of the columns of the basic feasible solutions are common? So why is that? That's because
M
this
minus 1.
n minus 1, right?
No,
Because this,
M.
no, n
The
minus,
rank of the matrix. The rank of the matrix was M cross N.
right,
Sorry,
right, yeah,
M.
yeah. So m minus 1 of them should be common, right? So here, in fact, yeah, so is this an n? Let's see. Yeah, this is an n, that's fine. F is a polyhedron Rn. And anyway, the remaining, like out of the n minus m in the basic feasible solution are equal to 0. So anyway, so n minus m of the coordinates of a basic feasible solution are equal to 0, right? So the one outside of that basis, they're equal to 0, so they're tight. So n minus m of them are tight anyway. Um,
M minus 1 are type for both of them.
Yeah, n minus m minus 1 will be tight for both of them, because first of all, whatever equation you have for the edge, it must contain either of these vertices. Um, yeah, so the general theorem that when we said that any vertex of a polytope in Rn will be determined by n linearly independent things, so there we had the general description that Ax is less than equal to b. So here we have to take both of them into account, the Ax equals b and the In x, that is x is bigger than equal to 0. So this is the matrix we wanted to consider. And this here we want to talk about n linearly independent rows here. Okay. So here, yeah, so this is a good question. I mean, here you had m plus n by n matrix. And essentially, we're trying to translate something about the column space to something about the row space. That is the whole source of my confusion right here, because I cannot say because the space we are in is Rn. So that's why I was talking about like a vertex being determined by n many of these constants being tight there and being linearly independent. So here, the vertex in the case of A, we were determining by setting. So you're choosing B1 through Bm. So these are all linearly independent. So A1, so AB1, ABM. These are all linearly independent. And so XB was nothing but AB inverse of B. And XB complement, let's say, was set to be 0. So these were all tight. And this corresponds to n minus m, linearly independent constants being tight at x. And And then you have
Both of them should have n-1 common.
both of them should have n-1 common, right?
Yeah, and also they have n-m-1 common.
Right. Yeah. So yeah, both of them should have n-1 linearly independent constants common. So including these sign constants. So let me just write v1 and v1 and v2 should have n-1 linearly independent constants, or rather n-1 linearly independent tight constraint common. And anyway, they have so n-m-1 of them are already common. So that's amongst those sign constants, n-m-1 are already common. So here, yeah. So what's going on here?
M is less than n. No?
Yeah, m has to be less than n because rank of that matrix is m.
Yeah, m. So in that case, it should be m-1 also.
Yeah. I mean, it is true, but the what is causing me some confusion is the transition from.
But these are the columns, no? And there we are talking about rows.
Right. Mm-hmm. Okay, so let's come back to this, like at the end of this lecture. So the like transition between column and rows is causing me some confusion. So for now, let's try to get up to like towards the end of the simplex algorithm, and then we'll revisit this. And this is a nice question, by the way. All right. So what were you talking about? Updated cost minus old cost. So if we choose the jth basic column to be added to these to this updated like basis ordered basis, which would correspond to a new vertex. So in that case, the updated cost minus old cost is this. And in order for this jth basic column to be useful for us, so in that sense, updated or to be like correspond to a vertex which is cheaper. So that would mean the updated cost is less than or equal to the old cost. Preferably, it is strictly less than, but less than equal to suffices for our. I mean, yeah. I mean, if it is equal, I guess we will always choose that option where it is strictly less than. So we want this quantity to be negative. So want j such that this is negative. Okay. All right. So now let CB be the vector in Rm, sorry, whose, this is just notation. So whose ith component is CBI. Yeah, and the reason we need this notation is because if I'm looking at a basic feasible solution outside of this index BI, the entries are 0. So if I'm looking at C dot X for a, so C dot X where X is a BFS corresponding to the basis B corresponding to B. Bm. So then since all the entries of X outside of this B are 0, so then whatever coefficient in the cost function you have that multiplied with 0 will give you 0. So I can just write this as summation from I equals 1 to M CBI XBI. The rest of the terms will be 0. So in other words, I can just write it as CB XB. So these are both vectors in Rm. X is a vector in Rn, C is a vector in Rn. But in this case, I can write this as CB dot XB, where both of them are vectors in Rn. So this is in Rm. This is in Rn. All right. And the vector Z, so this was the deficit that we had. This is the quantity that we had introduced, defined to be Zj. So Zj was defined to be Cj minus summation I equals 1 to m Xij Cbi. Okay, and this is what we want to be negative, and we have defined this notion of modified cost, which is difference. So Cj, yes, so the modified cost, so C prime was defined to be C minus Z. So this vector. And each of these entries, so essentially this is like, the jth entry is nothing but oh, okay, my bad. So Zj was defined to be this quantity, summation I equals 1 to m Xij Cbi, so that this is the differential from the original cost. So this is the modified cost function. So this is the modified cost. So C prime the vec is equal to C vec minus Z vec. And the jth entry is Cj minus summation j equals 1 to m Xij Cbi. Okay. So the theorem I want to prove is what we have been asserting about neighboring vertices, that we can use some sort of greedy algorithm to do our simplex algorithm. That means if I have no neighboring vertex which has a cheaper cost, a strictly cheaper cost, then my problem is solved. I'm already done. I just stay at that vertex. That is my optimal solution, and the corresponding cost is the minimum cost. So the theorem is that if C bar minus C vec minus Z vec is bigger than 0, bigger than equal to 0 at this vertex x0, at this basic feasible solution x0, then x0 is optimal. Okay, so this is kind of finishing off one aspect of the simplex algorithm. So what's the proof? Now let y be any element in the feasible set. Okay, so that by definition ay is equal to b, and we have y has all the sign constants. All of the entries of y are positive. Now let b1 bm be the current ordered basis. What does that mean? Because x0 is a vertex, so it has a corresponding ordered basis associated with it. It is a basic feasible solution. So that is the one I'm considering as the current ordered basis. Now for all j, Cj is bigger than or equal to Zj by our umbrella hypothesis, by hypothesis of the theorem. So look back, it says C vec minus Z vec is bigger than or equal to 0. So if you look at the individual entries, what it's saying is Cj is bigger than or equal to Zj. So that this is where we are going to use this hypothesis. So this implies that since these are all positive, yj is a positive quantity and Cj is bigger than or equal to Zj, we have this for all j between 1 and n. So our index I is always going from 1 to m, and our index j, it's about the columns of the m by n matrix. So A is a m by n matrix. So we're looking at the columns, and j is ranging over all columns. So we have this for all j ranging from 1 to n. So therefore, we have this cost at y. So y, remember, is an arbitrary point in the feasible set. And I want to essentially show that C dot y will be bigger than or equal to C dot x0. Okay. So if C dot y is bigger than or equal to Z dot y because of this. And so let's just write this as Z transpose y vec. Now what is Z transpose? That is nothing but CB, this vector transpose B inverse A. So there was a technical lemma that we saw in the end of the class. It was not very clear where we're going to use it. It was a very basic linear algebra result. This is where it's going to show up. Okay, so why is this true? Look at the expression for Z. Z is nothing but Xij CBI. So essentially, if I move the CBI here to the left, so you just think of this as CBI times Xij. So this is nothing but CB vec transpose. That is the entry CB1, CB2, that's the row vector, CB1, CB2, CBM. And then this is the multiplying it with the jth column of the matrix X. X was the tableau, right? So it is X, you are multiplying this with the jth column. Now this is nothing but you first multiply with X. So multiply this row vector with the matrix X, which is m by n matrix, and then take the jth column. There is no difference. And the result that we had seen in the previous lecture was that so X was in a very nice form, right? X was those you initially started with A, then every time you chose on ordered basis, you tried to convert it into some E1, E2, EM, like the B1th row, B1th column, you tried to convert into E1 using some elementary row operations. The B2th column, you tried to convert to E2, and then you got this matrix, this tableau X. Then when you kind of move to a neighboring basic feasible solution, yeah, so when we moved to a basic neighboring feasible solution, what happened was one of these columns was discarded, a new column, jth non-basic column was introduced, and that was converted into some EL. So X is corresponding to the new like tableaus where M of these columns are E1, E2, EM, right? And just as a reminder, so this is what we want to show. This is really, I'm claiming that the Z vec is nothing but CB transpose B inverse A. A was the original matrix which defined this feasible set, like with this AX equals B and X with sign constants. And what was B? B was essentially you take AB1, ABM. This is an invertible matrix, because that's we chose linearly independent columns for the, and these were an ordered basis for Rm. So this is our B, and here we're taking B inverse A. So I want to say that Z is in fact equal to this. So this is just a reminder. We have done this in the previous lecture. This is just a reminder. So what happened with X was it was a combination of pivots. X is equal to Ks, K1, K. So this was the first pivot. So you do some elementary operations and convert the ordered basis into like E1, E2, EM. Then you do the next pivot that will be given by another invertible matrix. You keep doing that. And then eventually after S pivots, you have reached X. Okay. So now, X, let's say Bj, yeah. So now if I take K, so if I call K equals Ks all the way up to K1, then now K ABI is nothing but EI. That's because you can think of A as this matrix, A1 all the way up to AN, and each of them, the kth column vector or the jth column vector of X essentially corresponds to K acting on the jth column vector of A. So now if I'm talking about KABI, so yeah, that is essentially converted to EI. So which means if I'm looking at this matrix AB1 all the way up to ABM, then I'm getting the matrix E1 all the way up to EM, which is the M by M identity matrix, which means K is nothing but B inverse. So if I call this B, K is equal to B inverse. So this X was nothing but B inverse A. Right. Yeah, I mean, so k is equal to B inverse. So all these operations, elementary operations that you have done to convert all this AB1, ABM to E1, E2, EM. So that corresponds to B inverse. So yeah, so just basic linear algebra. And since k is equal to B inverse, X is equal to B inverse A. And this is precisely what we have done here. So typically I should write Z vec transpose is nothing but CB vec transpose times X, but X is nothing but B inverse A. All right, so I hope you're convinced about this. And that acting on Y. But if I use associativity of matrix multiplication, I move the brackets around, I have AY, and AY is equal to B, because Y is a point in the feasible set. So I'll just repeat this. So far we have shown that C dot Y is bigger than equal to CB vec transpose B inverse AY. And this is nothing but B. So CB vec transpose B inverse B. Okay. Now what is the cost of X naught? The cost of X naught is C dot X naught, and that will be equal to summation I equals 1 to M CBI XI naught. So that's the one I had said that this is in Rn, but since X naught is a basic feasible solution corresponding to this basis B1, B2, Bm, so I had said C dot X naught would be something like CB dot XB. So forget about the zeros outside. So, and this inner product is in Rn. So that's exactly what we're doing here. Inner product of the vectors CB1, CB2, CBm with the coordinates corresponding to the basic columns. All right. So what is Xi0?
B inverse B.
Exactly. So you have this X10, Xm0. And the way we had always seen it that Ax is nothing but AB xb plus AB complement xb complement, but this is always a zero vector. So AB xb is in fact equal to B. So this is 0. So that means xb is nothing but AB inverse B. But in our notation, AB is just the matrix AB1, AB2 put together. And in our notation that we are calling just B, the matrix B. So that means xb is nothing but AB inverse B. And these are the entries of xb. So this, first of all, I can write it as CB vec transpose with this column vector x10, xm0, which is nothing but xb. And this is CB vec transpose B inverse B. And this is looking very familiar now. We have already encountered this right here. So C dot Y is in fact bigger than equal to C dot X naught. So what we have shown is C dot Y is bigger than equal to C dot X naught for all Y in F. Okay. So this finishes the proof of the fact that if so if at a BFS, like in whatever neighboring basic feasible solution you look at, that the cost is always positive, it's not strictly negative, then you're already optimal. X naught is already optimal. All right. And going back to the first question in this lecture, which we haven't answered so far, let me just remind you that our proofs are still complete. That was mostly to give an interpretation of when neighboring vertices, in this process that we have done, we have removed one of our basis element and added a new basis element so that we are converting a basic feasible solution to another. So my claim was that geometrically it looks like a neighboring vertex. So that is the one where there is confusion about this geometric interpretation. But in the proofs so far that we have done, like they're complete. So I don't want to leave you with the impression that there is something like missing in these proofs. I hope that is clear. But yeah, we still have to justify our geometric interpretation that like this operation that we're doing of pivoting essentially takes a vertex to a neighboring vertex. All right. So let me write it out. So the operation of pivoting in a geometric sense takes a vertex, by the way, which computationally corresponds to a BFS, to a neighboring vertex. And throughout in this computational algorithm, the word neighboring is never even used. It's not needed. It's just for our having a good mental picture of the process of what's going on. Okay. So I hope we'll be able to, if I cannot figure it out today, then in next class we will talk about it. That's the first thing we'll talk about, that this process of pivoting actually takes you to a neighboring vertex. Okay. So an important thing is done. So now, so the question still remains, like what basic column, what non-basic column should we choose? There is always a choice. So we have m columns, so n minus m columns are still remaining. And there's potentially many choices of non-basic columns to choose to add to this. And geometrically, which translates to, there are many choices of neighboring vertices. And we said, okay, we can use the cost function to make that determination. But let's see computationally how to do that. Okay. A quick corollary. So before moving on to that computation. So for all I between 1 and m, this is equal to 0. That is the modified cost of a basic column is 0. This is actually, this is not really saying much. It's just saying that if you're not changing your basis at all, so you're not introducing anything new to your basis. So remember, when we talked about modified cost, we were thinking about what if we include the jth non-basic column? What if you include the jth column? So j could have been basic or could have been non-basic. If it is non-basic, we had this whole operation that complicated matters. But if j is one of the basic columns, you're not really changing your basis at all. So the modified cost is just 0. There is no modification happening there. This is just something to observe. So I write it as a corollary, but it's a very trivial observation. Okay. So now let's write everything in the form, a new form of the tableau. So far, the tableau had this matrix A with A1, A2, AN, and then these entries B1 through BM. Now, noting that we have done some linear operations with the cost function. So let's see what happens if we put the cost vector as a row vector here and put a 0 here. Okay. So we put cost function as the 0th row. Okay, the first step we'll do, and after we write out the steps abstractly, we'll actually see a very concrete example so that this is very clear. So first put cost function as the 0th row. And then write Cj in the 0jth position. That's exactly what we have done. This is the 0th row, 0jth position has Cj. And place 0 in cell 0, 0. This is the 0th index. So you just place 0. So why we are doing this will be very clear. We have already gathered all the ingredients. This is just to do it in an algorithmic manner, figuring out what non-basic column to choose to add to our basis so that we move to a neighboring BFS. Okay. Now let B1 all the way up to BM correspond to a BFS. Now place EI in column BI via elementary row operations. So So far, again, the 0th row has not played any role. So even in the original method, we have been doing this. We were replacing EI in the column BI, and we had and then when we want to introduce jth non-basic column into there, we had tried to find out what the value of theta naught is. We took the ratio B1 over whatever was in that jth column, and then if it was negative here, then we just ignored. Wherever this was strictly positive, let's say we were talking about C2, we took the ratios B1 divided by that, B2 divided by that, and so on, and we chose the minimum value, and that corresponding L. So BL we removed and converted this into EL, the second column in this instance. So far cost function has not made an appearance. So number 3, now we will make some operations to the cost column. So for j bigger than equal to 1, cost row I should say, because I have written it as a row vector here. So for j bigger than equal to 1, so jth entry of row 0 is Cj minus summation I equals 1 to m xij. So essentially it's the modification of the modified cost, so which we wrote as Cj bar. So this is the jth modified cost. So column 0, rather I should say the 0th entry is now converted into 0th entry has minus summation I equals 1 to m xi0 cbi, which is precisely equal to minus, because this is the cost of the current BFS. So we have looked at it from many different angles, right? So here the cost was CBI xi0. So if I'm doing this operation where I'm taking the jth column, looking at the jth column, and I'm multiplying CBI. So you CBI with this matrix X and subtracting. Here I'm doing this to an extended matrix. So typically what I would do is multiply this row vector to this matrix X and subtract from C1, right? From this row vector. So, okay, let me just write it out. So you have this row vector C1, C2, Cn. I would subtract, so minus of, I would take CB1, CBM. So this is a 1 by n vector. This is a 1 by m vector. But if I multiply this to a m by n matrix, I'll get a 1 by n vector. So essentially, if you're thinking in terms of the computer, so I just identify this B1, B2, Bm. I create this new like sort of suppressed cost function. I'm ignoring some of the entries of this cost vector. And then I just multiply it with this matrix X that I have. In this case, I have A, so I'll just multiply it with A. Actually, I shouldn't say A, I have X, because I have modified by the second step. In the second step, I have done some elementary row operations to A and converted it into X. So the third step is essentially doing this operation, but to the extended matrix. Why do I say extended matrix? Because it is also including this column. So X, then I'll pad a B, vector B here. So this is now a m by n plus 1 thing. And here I would say, sorry, it will be m by n plus 1 thing. And here I would say 0. Okay, let me rewrite it to avoid confusion. So let me say what I'm doing is I'm thinking of the first row as 0, C1, C2, Cn. Then I'm subtracting CB1 all the way up to CBm times this extended matrix, which is B. This is the first or the 0th column, if that is the way we are indexing it. So this is the 0th column and X. So this, by the way, is a m by n plus 1 matrix. And this is a 1 by m. So this product is in fact a 1 by n plus 1. And this is also 1 by n plus 1. So the first entry of this 1 by n plus 1 vector is nothing but minus of this, which is minus cost of current BFS. All right. Okay, so I think I said it verbally, but I skipped writing it. So perhaps I will modify this to 4. This is number 4 actually. Like 3 and 4 combined, I just said it. So number 3 is essentially if J is basic, Cj bar is equal to 0. That's from that corollary that I mentioned. That modification, if J is a basic column, then the modification, the modified cost is nothing. Like you are not modifying the cost at all. Cj bar is 0. If not, then you are doing this operation that row 0 is sent to row 0 minus Cbi times row I for I equals 1 to m. So this is essentially telling you step by step how to do it. But in matrix notation, like if you're implementing it in Python or something like not using NumPy, then you would just write out this matrix and it will do that job for you. All these vectorization operations, it will do it for you. But in the book, for example, it will write it in 4 steps, 1, 2, 3, 4. So the way I said it, 3 and 4 have been combined because we are not treating b and x separately, but combining b and x as a single extended matrix and doing this operation directly. Okay. All right. So after doing this, you will have some modified. So you'll have the modified costs here: C1 bar, C2 bar, Cn bar, x here, and b prime. I should write b prime because remember, whenever we are doing step 2, doing elementary operations, converting a b1 bi to ei, b prime is in fact essentially giving you a recipe to read off the basic feasible solution. Okay, and here you get minus cost of current BFS. The BFS corresponding to this b prime. Okay, so let's see an example with some concrete numbers. So example, we are trying to minimize this objective function 10x1 plus 2x2 minus 4x3 plus x4 minus 2x5. And instead of telling you what the constants are, I'll just write it out. Write the matrix A out, so it will be clear. Anyway, the cost function has to be 10, 2, minus 4, 1, minus 2. And let's say the matrix is 8, 4, minus 12, 0, 0. So this is the matrix A. So 5, 2, 4, 11, 10, 1, 1, minus 2, 4, 5, and 8, 45, 21. So this is the vector B. This is the matrix A. This is the cost function C. And this is just some dummy thing you have put in 0 because eventually it helps us interpret after the computational process we do. All right. So in step 1, this is the way we set up things. Step 2. So let's say B1 is equal to 2, B2 equals 4, B3 equals 5. So essentially we have chosen the columns 2, 4, 5. So we have chosen this column, and this column. Turns out these are linearly independent. So what we really want to do is convert this into E1. That was our step 2. We want to convert this into E3. So after that conversion, so far we'll not touch the cost function at all. So no role has been played. The solution space is the same. We're just trying to find the vertex, not the neighboring vertex. So the column 2, column 4, column 5, they will look like the identity matrix. So in fact, here I can just put 0, 0, 1, 0, 0, 1. And after the appropriate row operations, we have minus 29 over 15, minus 1 here, and 2, 1, 3. So we're doing the row operations to this vector B. So this actually corresponds to the BFS. So what is the BFS here? So first of all, you have to put zeros in the first and second. So the corresponding BFS, you can read up from this tableau. It will be 0 here, then 2 here, then 0 here, then 1 here, 3 here. So this is the corresponding BFS. So 0 for the non-basic columns and 2, 1, 3, because it is in this order. Remember, in the previous lecture when we saw the example, like when the order got shuffled, so we had to shuffle this 2, 1, 3 appropriately to match that. So that's why whenever we talk about B1, B2, B3, we always specify order basis. For example, it could be true, we could have chosen B1 to B4, B2 to B1. So then it's a different basic feasible solution for us. So it doesn't just matter that it's 2, 4, 5. It does matter that we are choosing 2 first, 4 next, and 5 after that. Okay, so this is the corresponding BFS. And step 3, essentially we'll set these 3 things to 0 because these are corresponding to the basic columns. So here we are looking at modified costs. So we still have 2, 1, minus 3, 0, 0. So I'm just repeating the matrix X and the matrix, the vector B prime here. 1, 0, 8 over 3, 1, 0, minus 1, 0, minus 29 over 15, 0, 1, 2, 1, 3. So no different from what is below. So the thing I want to look at is the modified costs now. And for the basic columns, I have to put in zeros. Because if I don't change my basis, nothing happens. But if I choose this column, I can after I do the step 3, I'm left with minus 68 over 15. So how am I doing those steps? I'm essentially subtracting Cj. So these are the Cjs, right? 10, 2, minus 4, 1, minus 2. Those are the Cjs. Those are corresponding to the original cost function. Then I'm subtracting. So the modification Zj is equal to, or rather I should say Cj minus Zj, or Cj bar, let's say, to avoid confusion. That is Cj minus of summation Cbi xij. And that's exactly what we have been doing here. So Cbi essentially corresponds to these 3 numbers, right? 2, 1, minus 2. So you're taking for each column, so you're multiplying 2, 1, minus 2. For example, here, 2 times minus 3 plus 1 times 8 over 3 and minus 2 times 29 over 15. So plus 58 over 15. Let's see what that gives us. So minus 6 is like minus 90. Plus this is 24 plus 58. Okay. 2, 1, minus 2 over 15. Oh, sorry, this is 40. It looks like to be minus 8 over 15. Okay, I think it should be 8 over 15. But in any case, so the idea was that we need to look at the basic columns. So this was 2, 4, and 5, and then look at the corresponding numbers, 2, 1, minus 2, and then multiply it with the non-basic vectors. For example, here if you put 2, 1, minus 1, it should be 4 plus 1, which is 5, plus 2, 7. Oh, I see. Oh, the thing that's missing is, so we computed this term, then we have to do Cj minus this. So my bad. So Cj minus this. So if you're looking at the third column, what is the Cj there? That is minus 4. So it should be minus 4 minus this. Okay, so this is minus 8 over 15. So what I really want to put is minus 4 plus 8 over 15. So this is minus, oh, sorry, this was plus. So this should be a minus. So this is minus 68 over 15 of. So of course the book was correct. Yeah, so this is minus 68 over 15. So let me repeat. So to compute this quantity, what I did was take this vector 2, 1, minus 2 and do an inner product with this. From that, I got 8 over 15. And then I have to take Cj. J in here will be 3, so minus 4. Cj minus that quantity. So minus 4 minus 8 over 15 will be minus 68 over 15. Now let's do it for the first column, so as not to repeat any confusion. So in that case, so summation I equals 1 to m Cbi xij is what? It's you have 2, 1 minus 2. These are the cost variables corresponding to the basic variables. Then the vector is 2, 1 minus 1. That is the xij's. So 2, 1 minus 1. So this is 4 plus 1 plus 2. This is 7. Now I have to look at C1 because I'm looking at the first column. What is C1? That is 10. So C1 bar is 10 minus 7, which is equal to 3. So this will be 3. So why? So now that we have found this Cj bar, so essentially it is giving those, what is the interpretation of Cj bar? We want Cj bar to be negative, right? So J, that particular index J is telling me what non-basic column should I choose. For example, you can read off, you can see that I should choose the third column instead of choosing this as a non-basic column to move to a neighboring vertex, because if I choose this, what will happen is the cost will increase. And if I choose this column to include in my in a new BFS, then the cost will actually decrease. And by how much? By this times theta naught. I don't know theta naught yet. So that is also something that is lurking in the picture. But theta naught is always going to be positive. Like there is one small case remaining where theta naught was 0. So where you actually stay put, you don't move at all. Like instead of moving to a neighboring vertex, you just stay within the same vertex. So that is a case we'll consider in the next class. That will be the final touches on the simplex algorithm. That's the notion of cycling. You might cycle around and you keep going around in circles. And so essentially the algorithm never terminates. So there is a risk of that, but how to take care of that using something known as Bland's rule. So we'll see it in next class. But if that theta naught that we had chosen was strictly bigger than 0, then we had seen that this quantity theta naught times this will be a strictly negative number. So the cost will decrease if we add this. So, and algorithmically we have seen how to do this. And correspondingly here, we'll get a number. So what is that number? So xi naught times Cbi. So you just say 2, 1 minus 2, multiply with 2, 1, 3. 2 times 2 is 4, 1 times 1 is 1. So 5 minus 6 is minus 1. So here you'll replace it with minus 1. So here I will put it minus 1. So cost of current basic feasible solution is equal to 1, because it's the negative of whatever is there in there. But that also we can immediately see is because what is the current BFS? It is 0, 2, 0, 1, 3, right? So if I put the cost function 10 times 0, so that's why you can immediately see why that is happening, going to be the case, simply because the other like cost variables evaluate to 0. 10 times 0, 2 times 2 is 4, minus 4 times 0 is 0, 1 times 1 is 1. So again, 5 minus 6. So minus 1. Okay. So with this, yeah, cost of current BFS is minus 1 actually. So why did, then this should be actually 1. Right. Yeah, it is in fact equal to 1. It's negative of that. All right. So just encapsulate all of this in a lemma. The 0th entry of the tableau will always hold the negative of the cost of the current BFS of the current BFS, and the 0jth entry will always hold Cj bar. I mean, this is just encapsulating whatever we have just discussed. So 0jth entry will always hold Cj bar. For j bigger than equal to 1. Okay, if whenever we pivot, we perform a row operation so as to zero out the entry atop the entering column. So if whenever we pivot, we perform a row operation so as to zero out the entry atop the entering column. Okay. So yeah, essentially it's just saying that, so whenever we pivot, meaning that whenever we're trying to introduce a non-basic column, so we perform a row operation so as to zero out the entry in top of the entering column. So here, okay, so 0th entry will always hold the negative of the cost of the current BFS, and the 0jth will always hold Cj bar. So that's what we have seen. So this is Cj bar, the modified cost. Yeah, this is just describing what the process looks like, the pivoting process looks like. We're replacing BIs with EIs. Okay, so to end this lecture, as a summary, I'll just say how to pivot. This is the whole idea of doing this process was to figure out which non-basic column to add. So now we believe that we have this answer. So how to pivot? So first, find the column J whose row 0 entry is strictly negative. Whose row 0 entry is strictly negative, minus 68 over 15. That's what we saw. In fact, that is the only column you should be choosing, because the other column, other non-basic column, had a positive number in it. So find a column J whose row 0 entry is strictly negative. So what happens if there is no such column? That means Cj bar is bigger than equal to 0, right, for all J's. If there is no such column, we are done. Because remember, the first theorem we proved today was this: if Cj is bigger than equal to Zj, or in other words, if Cj bar is bigger than equal to 0 for all J corresponding to this BFS, then X0 is already optimal. Then we are done. No need of pivoting, nothing is needed. So if there is no such column, we are done. Two. Now we are talking about theta naught. So compute theta naught. So minimum over this set Xij strictly bigger than 0. No, this J has been chosen, right? So on that column, you find that index. So minimum of this quantity Xij. So here also an assumption has to be made that this is non-empty. Assume non-empty. So of course, here also there is a question that what if it is empty? What if there's no entry in that basic column, which is strictly bigger than 0? All of it is less than or equal to 0. In fact, in that case, we can show that this is an unbounded LPS. So which means an ill-posed LPS and not of that much interest, especially when you're talking about the minimization problem. Okay, so compute theta naught equals this. So if Xij is less than or equal to 0 for all I, so J is fixed, remember, J has been chosen in step 1, then LPS is unbounded. This will prove in the next theorem. So today we don't have enough time to prove that theorem, but like when we were talking about pivoting, we had already seen that whenever Xij is less than or equal to 0, that transference that we had done, Xi goes to xi minus theta xij, there we had no issues because theta could be chosen as large as possible, will still remain feasible. So here we just have to show that, yeah, so that even the cost function will blow up. So there we had no introduction of a cost function. We had just seen that theta could be chosen as large as possible and still x will be feasible. Now we just have to show how the cost function varies as we vary theta and send it to infinity. Okay, and the third step is find an L, because J is the column you'll choose, but we also need a column which we'll discard from our original basic feasible solution. So find an L such that theta naught is equal to XL0 divided by XLJ. So discard, so essentially discard column BL from BFS and include column J in BFS. And step 1 and step 3 have told us what is what column to include and what column to discard when we are moving to a neighboring BFS. So modulo the theorem mentioned in step 2, we know how to pivot. Mentioned in step 2, we have a recipe for pivoting. So this theorem that LP is unbounded, with regards to the cost function when we have this xij is less than or equal to 0 for all of these i's. So that will prove in next class. So pivoting we know, and then essentially we are pretty much done, except the fact that sometimes cycling may happen. Like even if you pivot to something which is different, some like basic columns which are different, but still the BFS, the basic feasible solution corresponding to that may be the same. So you're stuck in the same vertex, or maybe use a cycle around and come back to the same vertex. So we have to ensure some rule, some tiebreaker rule. So that also we'll talk about in the next lecture. So there are two main things remaining. And of course, the geometric picture that we talked about when we talk about neighboring vertices. So that geometric picture also will clarify in next class. So see you. Bye-bye.